Hello, TecQuipment and Partners. I'm Abby Brown here with Jordan Koch Pemberton, Brett Michael, Luke Moser, and Liberty Topka from York College of Pennsylvania's Civil Engineering Department. We are a team athlete and we're excited to present the following submission for TecQuipment's 2025 student competition. Our goal was to assess the impact of sediment and debris accumulation on infrastructure, infiltration, and operation efficiency through real-world simulation and the usage of TecQuipment H410. Our team started by collecting a water sample from an undisclosed landfill's stormwater pipe before it entered a detention basin. This location was chosen to evaluate maintenance practices and flow. Thanks to our connections, we requested access to the site. This allowed us to replace the H313 hydrology apparatus, as collecting water from this experiment would require pipe reconstruction. Instead, our group implemented a more practical method through the landfill water collection. The total runoff area surveyed for the site was about 717,000 square feet. The sloping benches of the landfill directed water flow towards the west, where it was collected by the downshoot that connects to a 60-inch concrete pipe. Both the pipe and downshoot are newly installed, having been in for only about 5 months. Water from the 60-inch concrete pipe then flows into the detention basin, which is the location from which our sample was collected. We then use the Viscosity and Particle Drag apparatus to assess the impact of this accumulation on infrastructure, infiltration, and operation efficiency.
As a group, we collected water for our experimental sample from the landfill as well as purified water from the lab. We noticed right away that the downstream collection is discolored, filled with impurities that vary in size, and doesn't seem to want to settle, whereas the purified water is clear and free of debris. Here shown on the slide are pictures of the landfill or site that we took the water from. Down in the bottom corner, circled in red, is where we collected the stormwater runoff through a 60-inch concrete pipe that fed into a detention basin. The blue arrows are the way the water flows down the site. It flows into a downshoot, which is then directed into the 60-inch concrete pipe.
At the bottom of each tube, there's a valve that allows for you to collect your sphere and dispense your fluids after you have conducted your experiment. From this apparatus, you can ultimately get kinematic and dynamic viscosities, as well as corrective velocities for the two liquids that you are comparing. For our procedure, we poured our two liquids into the parallel tubes and then recorded our 1 meter distance and marked the distance off with tape. We then dropped our balls one by one into the tubes and recorded the time it took for each ball to travel the 1 meter.
Using these recorded values, we were able to average the time and calculate a corrected velocity using the Apparatus manual's corrected velocity equation. We did this for both the purified and stormwater and found a velocity of purified water to be 0.127 meters per second and a stormwater velocity of 0.122 meters per second.
Using an equation found in the apparatus manual, we can calculate the dynamic viscosity. As shown in the slide, you can see how the ball density and the liquid density were utilized in this equation, which were found previously. After computing this equation, you can see mu, or dynamic viscosity, equals 0.0289 Pascal seconds.
Also using the apparatus manual, we can find a kinematic viscosity, which is simply just the dynamic viscosity divided by the density of our stormwater. After we do that calculation, we find a kinematic viscosity value of 0.0258 centimeters squared per second.
Using the computed values from the prior page, we were able to compare them to known values for the kinematic and dynamic viscosity of purified water. As you can see on the slide, the stormwater experienced more viscous forces on its fluids, meaning that it won't travel as easily through drainage pipes. Also on the results page, we have a chart featuring the percent difference. So this is the overall difference between the two velocity values for purified and stormwater. Even though they differed slightly in magnitude for the values, it still shows that there was a slight difference between the two velocities, with stormwater being slower, which can be proven by the fact that it had debris accumulation in it.
As previously discussed, the results achieved align with our expectations that stormwater drains at a slower rate than purified water, primarily due to the presence of obstructions such as dirt, grass, and other small particles within the sample. This observation underscores the critical role of placing sediment traps, particularly before the entry of the pipes, in allowing proper flow. During certain phases of the experiment, challenges were encountered in retrieving the specimen due to sediment buildup at the bottom.
From a real-world application standpoint, pipes containing debris will experience lower velocities and viscosities than cleaner water. It is important to account for these discrepancies when designing storm pipes.